Earth is accurate enough to detect gravitational waves from pulsar timing from different directions, which I think is a very exciting field. And they wondered if they had to estimate where the Earth was relative to the solar system barycenter, because we don't know it accurately enough. And so I think I convinced Joe and a couple of others that we do know it accurately enough that the pulsar timing is not likely to contribute, which on the good side means that your pulsar timing, you can use that to look for gravitational waves instead of the orbit of the Earth. But on the bad side, it means you don't get to determine the orbit of the Earth. So that's sort of the background for this talk. I'm going to try to tell you something about how we model the orbit of the Earth and the planets, why we do it, how well we do it, but I'm going to try to pitch more towards aspects of general relativity and gravity theory that we can test with our data. We don't normally set out to test, the ppn gamma parameter when we look at Mars. We're more interested in getting data back from the spacecraft at Mars. But we can do that on the side, and so that will be of some interest. So the planetary ephemeris, as we model it, consists of 8 planets, because Pluto is no longer a planet, it's a dwarf planet, but we include that in our planetary ephemeris. We model the effects of 343 asteroids out of 200,000 plus asteroids. We find these 343 have the biggest influence on the orbit of Mars, and the other 200,000 minus 343 account for about a little less than 10% of the mass of all the asteroids, and their effect on the orbit of Mars is less than a meter, so we can't really measure that today. So that's how we picked a set of 343 asteroids. The other dwarf planets, besides Pluto, which is now a dwarf planet, include Ceres, which we include as one of our 343 asteroids that we model. The Kuiper Belt objects, which I ignore in terms of integrating the orbit of planets, Sedna, Eris, Haumea, Makey. And so Mike Brown down here thinks there should be several hundred other dwarf planets, but the IAU, the International Astronomical Union Committee that meets to decide what is a dwarf planet and what isn't, hasn't met for 10 years now. And so these 5 are the only official dwarf planets, even though there's other objects that are probably bigger and closer. Yes, this is very informal. Just butt in any time.
So this is all relative to some solar system barycenter.
So I'll talk about what I think the solar system barycenter is, but I actually measure mostly to the sun because I can tell where that is. Okay. But we'll talk about the solar system barycenter because people think that exists too.
But is there any interest in sort of measuring proper motion with respect to some galaxy?
Proper motion, so...
with respect to some of the galaxy.
So I'll talk about the motion with respect to the galaxy. Currently don't model it. So I'll explain all the forces that we model and the forces that we don't model and how big the forces we don't model are, and whether the motion around the center of the galaxy is detectable or needs to be modeled or not. So that'll come up shortly. So I'm not putting it off, but I might as well go in a little bit of an order. I am going to jump around a little bit here and there. So I want to point out there's 3 centers around the Earth that estimate the orbits of the planets. So besides JPL, there's the Institute of Applied Astronomy in Russia, and the IMCCE, I call it, because I don't do French very well, in France. So we all, the 3 of us, generate numerically integrated orbits of the planets because no analytical theory has enough terms to fit all the data to the accuracy we can measure now. JPL is a little bit different because we estimate our orbits of the planets at the need of NASA spaceflight projects. So for instance, tomorrow I have to deliver an updated orbit for Pluto to the New Horizons project because they're planning a trajectory correction maneuver. They want the best estimate they can get as soon as I can give it tomorrow as the deadline. Whereas these other institutions are mostly playing around in my view. However, we all have the same data set. We're all using the same equations of motion. We all know how to fit all the data, and so our ephemerides are all more or less the same. I consider all the differences within our uncertainties. So where we differ, them and I, is that I care very much that our uncertainties be real uncertainties, and they would rather have the smallest uncertainty they can publish. Now, that doesn't make any difference in practice. If you're estimating ppn gamma and you get gamma minus 1 is 0 plus or minus 10 to the minus 4 or 10 to the minus 6, it doesn't make any difference on the orbits of the planets, it's just on what you publish. But it makes a very big difference to us at JPL and NASA in general, because if we're sending a spacecraft to a planet, we want to know how well do we know where that planet is. And so lots of times, like the Pluto mission coming up, is going to fly by Pluto, and they say, well, how uncertain is Pluto's orbit known? Because we want to take a picture of it. And if we don't know very well, we have to take a raster of pictures around it to make sure we get one picture at least. And so that's what this indicates. And so we try to give them the best estimate we can, But we want to give them the right uncertainty too, because if our uncertainty is very large, then they'll take a lot of blank pictures. And so that's bad to take a lot of blank pictures because it's very expensive, all those pictures, and sending all the data back to ground. On the other hand, if they're all blank, that's even worse than if 99 out of 100 of them are blank. And so I've been trying very aggressively to make an estimate that I think is about 1 sigma. So the probability of getting a picture in a two-dimensional plot is about 80% on that 1 pixel. And typically they will triple that. And so if too many people triple the uncertainties, give 3 sigmas of 3 sigmas of 3 sigmas, you get a lot of blank pictures. So I try not to do that. So my measure of success is not the smallest estimate I can give or the biggest estimate I can give, but whether they come within about 1 sigma off, right? Because if they come in right on my estimate, then I was too conservative. So I use a different figure of merit. And I'll show you some of the effects of that. Okay, so the equations of motion we use are the Einstein-Edenfeld-Hoffman equations, published 1938, as modified by Clifford and others over years to put in the post-parameterized Newtonian parameters in here. And so these are all pretty normal. There's a little bit of uncertainty. These are only good to order 1 over c squared. 1 over c to the 4th terms are too small for us to measure, so we just ignore them. There's terms in here that depend on the acceleration of the body, and we just use Newtonian acceleration because we're too lazy to iterate the second order effect because it just doesn't matter. So these are the equations that we use, but we need them to fit the data. We need this sort. If we just tried some Newtonian approximation with Newtonian perturbations from all the planets, we could not fit orbits anywhere near well enough to meet our requirements. So the tidal forces, the fact that the sun is oblate, the moon is oblate, the earth is oblate, we have to include all of those, especially for the orbit of the moon, because with lunar laser ranging data, we measure the distance from observatories on the earth to different points on the moon where there are retroreflectors to a centimeter. So we're very sensitive to the distance to those retroreflectors and the change in the orientation of the moon. And that's very, very strongly tied to these tidal interactions. On the other hand, the tidal effect of Jupiter we ignore right now. If we have a little better data for a spacecraft to Mars, we might need to take that into account. So that's an improvement we're planning for the coming years. So the acceleration on the Earth, I've calculated here things that were not being modeled. So we're not modeling 190,000 odd asteroids because we think the uncertainties in the mass of the 343 that we do model is so large they can suck up anything about the others that I don't know. So some people use a ring of asteroids. That's sort of traditional, just a ring mass. And I don't like to do it because anybody who's read Ring World knows that the ring is unstable, right? And so it's not dynamically consistent to have a ring. And so I don't have a ring. Both the Russians and the French have a ring, and I don't keep it. The French are very proud that their ring is allowed to change orientation, but it's not allowed to slide back and forth. So we all have different approximations, but they're all good enough. So the Kuiper belt objects, the GM of Eris acting on the Earth gives us about 10 to the minus 14 meters per second squared, sort of LISA, the drag-free control level that we might care about. But we can't see that with the current data we've got now. The Trojan asteroids I've even only dreamt about at night. I have no idea how many there are, how big they are, but they don't affect the orbit of the Earth enough for me to measure. I would see a signature that I don't. And so I don't lose any sleep about it, but I think about it sometimes. Sunlight acting on the Earth, right? The sunlight is pushing the Earth away at 10 to the minus 16 meters per second. So we can't measure that, and so we currently ignore it. I'm thinking of adding in just for completeness because it's simple enough to model with sort of 10% accuracy and say, yes, we do include it now, but it makes no difference. The oblateness of Jupiter, like I say, acting on the Earth is 10 to the minus 12 meters per second squared, and that's something we can easily measure if it's acting on the Earth or the Moon differentially or on Mars, but it's just about the level where we care about. So the next year or two we'll be adding that term in. And so if we ever do laser ranging to Mars, which some people in NASA very much want to do, we will have to include this effect to get an answer that's correct, although we'll be able to fit the data without it. Okay, the rotation of the galaxy. The sun is rotating around the galaxy with a period of 250 million years. And so it's far enough away that 250 million years, v squared over r of that is 10 to the minus 10 meters per second squared. So that's easily detectable, except it's acting on every body in our solar system almost the same. And so in a sense, it's sort of freely falling in orbit around the center of the galaxy, so we don't have any differential motion that we can detect. But the fact that we're moving around the center of the galaxy is starting to become detectable, right? And so if we look at positions of quasars, extragalactic radio sources, with VLVI, some people believe, and I believe, they can actually see that the direction is changing slowly with time because we're moving, so many nanoradians per year relative to the space. So we need to start modeling that, at least for the VLBI community, pretty soon. Dynamically, I don't know that makes any difference or not. So I'm starting to think about that. So I'll worry about this after I worry about the J2 effect for Jupiter.
So when you exclude things like this, is it mainly in terms of instantaneous forces, or do you have to worry about resonances anywhere?
So we do this all numerically so that the resonance is all part of the computer program. And so we don't explicitly model, any frequency associated with anything.
No, but if you're not putting things in, you don't know.
That's right. So for instance, the Kuiper belt. If the Kuiper belt is a sphere of objects of uniform density, then they have no action on the solar system. And so ignoring them is negligible, right? And so if it's not uniform, then maybe it causes a problem. Okay, so I'm listing the things here that we don't include because we don't think they're important, but we could be wrong. Okay, but in terms of predicting where Mars is a year from now, they are negligible. Right, we're sure of that. But the distance to Mars measured in absolute meters, maybe we're biased, by a part in 10 to the 12th. Right, but that's small enough that we couldn't see it hardly. Okay, so the lens steering effect is something a young colleague of mine is starting to worry about, because if we could detect it in motion around another planet, then that would be important. So there's a guy named Lorenzo Iorio, some of you may have heard of, that has predicted that this effect should be detectable. And in fact, we currently think that for the Juno mission in orbit around Jupiter, the lens steering effect will be a big measurable effect on the orbit of the spacecraft. So it will precess and perihelion due to lens steering every time it comes by Jupiter, screening above the cloud tops. And that turns out to be a very useful number at Jupiter, because measuring the lens steering effect should be proportional to the moment of inertia of Jupiter, the angular momentum of Jupiter, the moment of inertia times the spin rate. And the moment of inertia is a very important number for constraining the interior structure models of Jupiter. So we're very grateful to Lorenzo for pointing out the lens steering effect can be important, because for Juno it is. So for Mercury, the effect of the lens steering effect is about 7% of the effect of the solar oblateness. But the effect is almost identical to the effect of the solar oblateness. So pulling them apart looks like it's just about impossible right now. So this is a plot I pulled out of Lorenzo's paper. This is the effect of the lens steering effect on the range from Mercury to Earth as a function of time. And it looks a lot like the effect of the solar oblateness on the function of time that he plots on the next page. So if you put them side by side, you say, gee, they look a lot alike. And in fact, if you turn this one upside down, they would look even more alike. Right? So a little bit of decrease in the J2 looks exactly like the lens steering. So we don't currently model it. It's a 7% effect of the J2, so it's within our measurement capabilities easily. We just can't separate it. So for right now, we're ignoring the lens steering, but we'll put it in the near future. But whether we can estimate it or not, I don't know. It looks like if we fix the value of the J2 of the Sun from helioseismology, which seems kind of fair, then we can detect this effect with confidence, but I don't know whether that's interesting or not. It's cute, but maybe not important. Okay, solar system Barrier Center. Getting back to your question. So I defined the solar system Barrier Center using the invariant quantities from the PPN metric, right, which Frank Estabrook here worked out a long time ago. So this is the position of what I call the solar system Barrier Center, and this is where these masses are the relativistic masses from the PPN metric. Because tidal effects, so I take this, and at my first initial integration time, which is very strangely picked to be June 1969, and that's chosen because that's before the first lunar laser ranging measurement. So you can analyze lunar laser ranging data only integrating forwards in time from that point. So that's sort of a historical oddity. So I set this number to be 0. So I adjust the position of the Sun and planet, so this adds up to 0 at the initial time. But I propagate them forward in time with not just the PPN metric, but with the tidal effects, particularly the J2 of the Sun. And because of that, this term is not constant in my integration. It actually drifts off a little bit. Okay, and so what I call the center of integration is different than this evaluation of the solar system Barrier Center. The other thing is, the Barrier Center calculated this way depends a lot on which bodies you include in your summation. So for instance, I'm ignoring Sedna, right? And so my Russian colleagues include Sedna, and so their Barrier Center is 50,000 kilometers different than mine, because even though Sedna doesn't have much mass, it's way the heck out there, and so it affects the Sun a lot. Okay, so the distance from the Earth to the Sun that I estimate is the same as she estimates in Russia, but the distance from the Earth to the barycenter is very different, okay? And so what matters to me more is that the center of integration be a quasi-locally free-falling point that's convenient, right? And numerically it would be awkward to put the solar system barycenter 50,000 astronomical units away because I would have numerical precision problems handling it, but it could be anywhere. Okay, so that said, so this is the effect of the tidal terms on that particular computation, and I'm not a good enough mathematician to try to find an invariant of the ppn metric combined with the J2 of the sun. And so I'm just going to live with this fact that what this barycenter calculation gives drifts off by a few millimeters over a century. Okay, so it's a known effect. I can't measure a few millimeters in a century, and so I don't care, but I'm trying to be honest about it. Okay, but how well do I know where the Earth is relative to the barycenter, whichever barycenter you want to pick? And so I did this study for Joe and Michele and his colleagues about pulsar timing. So I worry a lot about the uncertainty of the Earth relative to other things, and so here I'm plotting the uncertainty relative to the sun. So this is the uncertainty in the distance from the sun to the Earth as a function of time, and so it's a little under 2 meters. And so I know the distance from the Earth to the sun to a few meters. The uncertainty in the distance of the sun relative to the barycenter, which the way I calculate the barycenter is very near the center mass of the sun. So that the uncertainty in that distance is much, much less than a meter. Okay. The uncertainty here is in the right ascension and the declination of the sun. And you can see that in right ascension, it drifts off with time a little bit because I don't know the semi-major axis perfectly, so that's what the drift is. And the fact that this is not centered on zero is because the solar system as a whole is a dynamical system that I evaluate by measuring range measurements from Earth to various spacecraft to various planets. But I can rotate that whole system and the range measurements are invariant. And so there's some uncertainty about how I want to align the planetary ephemeris coordinate system with something. And so this is my ability to align it with radio sources that the IAU VLBI people define their reference frame with respect to. So this is just limited by our accuracy of determining the direction to Mars relative to a quasar. The relative angular positions of the planets are much better known than this, at least the inner planets, but I can't tie them to the quasars more accurately than this. Does that cover your barycenter adequately?
I was curious also, is the barycenter sensitive to your solar model? I mean, does it lie outside the sun or is it inside the sun?
The barycenter calculated this way, the sun moves through that point every few years. But it's out, it's about a solar radius away from the center of the sun. But the sun oscillates through it and back. So sometimes the difference in distance between the position of the sun and the barycenter calculated this way is zero.
And that, because it goes inside and outside the sun, it depends on the solar composition. I mean, the amount of material near the radius of the sun. So you know that well.
Well, so let me back up again. If I included 7 with my estimate, right, I would move the barycenter farther away, and so the sun wouldn't come near it. Okay, and so to me the barycenter is not a physical point, it's just a construct. Okay, so we're very sensitive to the GM of the sun, the mass parameter of the sun. We can estimate the mass of the parameter of the sun to about a part in 10 to the 11th, but we can't tell you what it's made of. Right, we can't tell you how big it is hardly, except through the J2 oblateness times 1 over r cubed. We can tell you about that product. Right, but we can't tell you whether it's made out of hydrogen or iron. Not this way. Okay, so I worry a lot about time scales. I don't know if you guys worry about time scales. Over time, people have worried about defining ephemeris time, and so ephemeris time 100 years ago was defined, and then barycentric dynamical time, TDB, was defined, but it was defined before people really said, oh, we need to use a coordinate time from a ppn metric. Right, and so TDB as defined that way was not that kind of time. So JPL introduced our own time for a lot of years, starting in 1984. We used our own time and said, well, TDB, however it's defined, which is kind of loosey-goosey, is close to what we use. Okay, so a bunch of theorists said, okay, we're going to redefine TDB to be a coordinate time in 2003, but they introduced a new coordinate time called TCB, barycentric coordinate time, which is based on the fact that this is a metric, or a unit metric interval. And if for TDB, we choose this scale factor, L sub b, so that ephemeris coordinate time near the Earth ticks near the rate as atomic clocks on Earth. That turns to be extremely convenient if you have a lot of measurements made on Earth, which so far all of our measurements are. Okay, but the theorist said, oh, this is an ugly L sub b, we don't like that. So if you take that away, you get barycentric coordinate time, and you can integrate everything in barycentric coordinate time, TCB, and get exactly the same differences, except time runs away from our clocks pretty rapidly, right? And so if you want to look up a position of a planet today from a TCB integrated ephemeris, you have to subtract like 70 seconds or something from the time you calculated for your atomic time. So it's easy to make a lot of mistakes, but it's prettier. So they redefined TDB to be TCB plus an estimatable scale, and then 3 years later they said, no, we don't like that estimatable scale, we'll just fix the scale. And so now TDB drifts away a little bit from atomic time on the Earth because of this scale, but we don't really actually know that perfectly, and so the difference is small enough. So we use this TDB coordinate time, but the other people like TCB. What depended on gamma?
The metric time.
Yeah, but gamma is 1. Well, I'll show you some estimates of gamma. All right, so there's all these different time scales that we have to worry about. There's TT, which is an offset from atomic time. TAI is atomic time. It also used to be called TDT, but it's no longer called TDT. It's called TT now. And that's a coordinate time for some strange metric where the Earth is the only gravitational object in the universe, and they do this for Earth orbiting satellites. And I have a little trouble wrapping my mind around that. But if you look up the coordinates of a GPS satellite, right, then it'll probably be in TT time. But since it's close to TAA time, then that's okay. But TCD time then is up here is a fixed ratio from TDB. But then they had to introduce another coordinate time for Earth satellites that wasn't TT. Right, so they want to scale TT so it doesn't have that L sub b and the metric equations for Earth orbiting satellites, and so that's what TCG is. And I don't know anybody who uses TCG, but we all argue about what these times are and what people work, because it matters in terms of measurements of pulsar timing, for instance. You need to know your times to like a nanosecond, and so what time scale you use really is important. And so we do everything in TDB, and we promise NASA will never change. So TT minus TED is a quantity we need a lot, and this is an expression that's reasonably good that you can find, but you need better expressions, and when you get down to pulsar timing, you probably need to integrate the actual equation of time difference between ephemeris time and atomic time, and we just recently started distributing that as a numerically integrated quantity. All the value that was integrated 20 years ago for the ephemeris DE405, as far as I can tell, is just as good. But some people wanted it there, so we put it there. Okay, length scales.
How well do you know the delta?
Sorry?
How well do you know the delta?
So we certainly, a bias is not really estimatable, okay? But a change in this time scale of something like a nanosecond over a month we would notice. Okay, but anything slower than that we probably couldn't tell exactly. And I didn't bring a plot, but if you plot this as a function of time at the center of the Earth, there's a drift there introduced because the theorist made L sub b be a fixed number. There's a small drift that varies a little bit by the estimated mass of the solar system. Okay, and so if you include the asteroids or you don't include the asteroids in your integration, you get a little slightly different number. It's not big enough to affect anything at the nanosecond level, right? But certainly at the picosecond level. But mostly we care about time differences, right? The difference between now and a time for satellite tracking. Well, 18 hours to Voyager is the longest time I've ever heard of. But normally we don't care about time differences over very long. All of our measurements are like the time between we transmit a signal and the time we get a signal back. So any big bias or any big rate will difference out in that kind of a measurement processing. Okay, the length scale. So thank God somebody finds the speed of light is a fixed number in 83. That makes our life a lot easier. But we've been arguing for the past decade about what an astronomical unit is. And so people since the time of Newcomb in the 1900s were saying, well, how far is the Earth from the sun? And so they defined it for a long time. The astronomical unit was defined, I'm not sure I can even say this. It's the same major axis of a massless object orbiting a sun whose GM was this number. That defined the AU. That had a period of a year. right? And very, very few people knew that, but we argued about what an AU was for a long, long time. And so finally in 2012, I convinced the International Astronomical Unit, let's pick a number of meters, and we'll just say that's an astronomical unit. So right now, that's what an astronomical unit is this exact number of meters. It doesn't matter what time scale, it's just the meters, it's just a number. There's currently a working group formed to define a canonical solar mass for use for planets orbiting other stars, right? How many solar masses are there? People are using different masses depending on what they look up in a book. So they want to find a standard solar mass. So we'll pick some number. So this actually is within a part in 10/11th of what we were estimating before. We just now codified it. So the JPL planetary ephemeris is integrating distance of astronomical units. Now it's very convenient to do that if all of your measurements are just directions to things, because the system can all scale up then and down in distance and all the directions are stay the same. But now all our distances to planets are based on round-trip line time, and we can't just freely scale that anymore. So we integrate in astronomical units just for historical reasons. We all store it numerically as kilometers, because that's what everybody wants in the end when you're doing light times. Okay. We also use light propagation, so we use this expression from Ted Moyer. I'm sure there's lots more accurate calculations of you count the integrated light time along a path bent by the sun and other planets of the solar system. There was some controversy some time ago about when light was deflected by Saturn, when was that deflection? And this is related to that, so there was some going back and forth about whether this equation is good enough or not. It's good enough for our range measurements today, and so we get sensitivity to the gamma here from the light time, the Shapiro effect, right? Erwin Shapiro effect predicted that a long time ago. So I'll show you some estimates of the gamma that we get. Okay, so now I'm down to the reference frame. So if you look up in the stars at night and take a time-lapse picture, they all make a nice little circles on the sky and say, oh, there's the North Pole of our coordinate system. But if you went the next night and took a picture and tried to overlap them, they wouldn't quite overlap. And so for a long time, up until 1988, in fact, people were saying, well, we'll just take the path that the sun goes on the sky and the ecliptic and the equator, and that defines our coordinate system. But that's based on an average, so the mean Earth orbit. Well, what's the mean Earth orbit? The mean Earth orbit is not periodic, because perturbations from Neptune and Jupiter cause the mean Earth orbit plane to tilt, right, all the time. And so the average that you get depends on what estimate you used and how long you averaged it over. So finally, back in 1988, I think, 1987, the IERS, the International Earth Rotation System, well, forget all that. We're just going to pick that quasar and call that zero. All right, and so they expanded on that and picked a set of quasars that are well observed and say, we'll pick all the zeros, and we'll pick one that's zero that's close to the intersection of the Earth mean, equator, and equinox of J2000. Okay, it's close, but in fact it's 55 milliarc seconds off. But we didn't know that at the time because we didn't know that intersection with that level of accuracy. Even we knew the relative positions of quasars to much better accuracy. And so we just allowed this number to be an offset. So that has a little bit of implications for theories of the precession of the pole of the Earth, but for us it's just a number we have to subtract. So VLBI is...
So that defines a zero longitude, but there is no precession.
So the zero, it defines the zero of the coordinates on the sky. Okay, but in that definition is assuming that the sun is fixed relative to the quasars, which it isn't because of the rotation around the galaxy. And so that's going to have to be taken into account into the next realization of the celestial reference frame. Right? They're going to have to pick a time at which that quasar is zero. Right? Because
what I was asking about is something different. I was asking about the precession, about
the precession of the Earth's pole?
Yeah.
Yeah.
And you do have to still take that into account, right? That's still...
You have to account for that when you reduce the data, right? You have to know where your tracking station is in inertial space.
You're not getting away from that.
Right.
Still 2,000 up or whatever.
Right. So the definition of longitude is a little bit interesting history. I don't want to go into that right now. But it used to be Greenwich Observatory defined longitude zero. And so the longitude...
The celestial longitude.
Oh, celestial longitude. Well, so it's defined by a set of quasar positions. And so when they measure quasar positions better, then they can't compare it to the old one with the new measurement accuracy. And so they try to be near it, right, as well as the old measurement accuracy was. But it might have shifted a little bit, and we wouldn't necessarily know. So they allow it to wander a little bit to the measurement precision. Okay? So radio telescopes, like Joe works on all the time, measure noise signals from quasars, and measures the difference in the arrival time of those quasars by recording the signals open loop and correlating them post-processing to find the differential arrival time. And if you have a good enough time and a good enough knowledge of the baseline and watch enough quasars, you can construct a self-consistent system, but you have to define a coordinate system somewhere. So you could pick one antenna on Earth to be longitude 0 and wrap everything around that. But instead we define a set of quasars to define longitude 0 on the sky and estimate where the stations are on the Earth. So that's how longitude comes in, is through the definition of time eventually. But the LBI is not perfect because quasars, these are images of quasars. Quasars are not point sources. They're now resolvable. As you get better and better imaging, you can say, oh, that quasar's 3 things instead of 1 thing. And the average position of that depends on when you looked at it, and depends on which baseline you used to look at it. It gives you a different projection across these curves. So our coordinate system's not perfect. The current quasar accuracy is, I think, good to 0.2 milliarc seconds. Some people think it's a little better than that. And we use the same technique to look at signals from spacecraft relative to quasars now, for spacecraft orbiting Mars or Venus or Jupiter, to get the directions of those planets. And that's how we tie the coordinate frame of the planetary system to the quasar frame. So that's something I've been intimately involved with for the last 25 years, is doing VLBI measurements of spacecraft at Mars since 2001 when we had one go into orbit around Mars. Because what we care about mostly in the planetary ephemeris development at JPL is trying to get the spacecraft to land on Mars right. Because if we're wrong, then it crashes, and we don't like that. But they also say, well, we don't want to land on Mars, we want to land on this part of Mars, right? We don't want to land on this flat plane, or we want to land in that area, or we want to land in this crater. And so they keep putting tighter and tighter demands on where on Mars we want to land. And so we've in fact improved the accuracy with which we know where Mars is relative to Earth by a factor of 1,000 over the last 25 years. And we've done that by taking VLBI measurements of spacecraft with ever-increasing technological improvements. Part of the improvement is getting an internet line out to Goldstone. Allows us to send more data back to have more signal on the arrival time of quasar signals at the DSN telescopes. And then,
so it's the same telescopes that you use for quasars and for spacecraft.
That's right.
Very same setup.
Yeah. And then they started digitizing the signal at higher frequency because analog effects on low frequency signals are more important than analog effects on high frequency signals. That they're related to the bandwidth. And so over time you can see the noise of these measurements is improving. And so currently we can tie the Earth's orbit to about 0.25 milliarc seconds. Not quite as good as the quasars themselves, but close enough.
So that means you do quasars in the Ka band or M band? Or...
Well, so we do the spacecraft in X band because that's what they transmit. And so we care most about where the quasars are in X band, because the spacecraft are at X band. And so the quasar catalog right now is defined by XS, right? Because the dual frequency stuff takes the solar plasma out and the ionosphere out, but it's the X band position. Most of our spacecraft don't do X and S. So we really care about the X band positions. X band is 8 gigahertz roughly for anybody who cares. And so I've been telling people then for the last decade, we don't have to do any better than this. Finally. So even if we could do better now, it doesn't matter. And that's because the spacecraft landing on Mars always comes down on a parachute. So it's floating down on a parachute for about 100 seconds. And we don't know what the wind speed on Mars on the day it's going to land is to about 1 meter per second. So if the wind speed is blowing 1 meter per second times 100 seconds, it's going to drift 100 meters. And it doesn't matter if I know where Mars is to 1 meter, because it'll drift on the parachute. So I'm not trying to do better than this ever. People will try to do Ka band quasars to do better. But in terms of landing on Mars, what you really care about then is I want to land this rover next to that rover. So you need to come on board and land next to that rover, and you'll have to control the parachute so that you do it. But in terms of inertial accuracy, we're not going to have to do that. Okay, let me talk about what we estimate. So lunar laser ranging is the best measurement technique we have for measuring the objects off Earth. So there's 5 Earth tracking stations that have been used over time to measure round-trip light times to 5 retroreflectors. I'll show you a picture. There's 4 of them that we've been using for a long time. The 5th one, Lunicod 1, was launched, and it moved around. It was a rover, and then they lost track of it. And so it was nobody could point a laser at it for about 20 years. And then finally, when the Lunar Reconnaissance Orbiter went into orbit 5 years ago, they took enough pictures of where it ought to be that they found it. And so now laser range measurements are made of that rover again. So we have 5 points. The round-trip light time we measure from the station to the position of the Earth on the Moon depends on all these factors: the rotation of the Earth, general relativity, the atmospheric pressure, etc. So all those things have to be taken into account when you fit the data. the measurements accuracies improved with time. These are pictures of the 3 Apollo retroreflectors, and there's 2 Lunokhod reflectors. These were built in France and launched by Russians on rovers, Lunokhod 1 and Lunokhod 2, here up in the north. And so they help determine the orientation of the moon a little bit better than just the Apollo ones, which are a little more equatorial. So the accuracy of the measurements is improved in time, I'll show you on the next plot, to the point that it matters trying to guess which of these array of corner cubes, which are all about the size of your fist, which one of them reflected the photon back. Okay, that's now probably the dominant error source in the measurements. So if we can make one bigger corner cube, we can improve the measurement accuracy. And so a number of us have thought about how do we do that. So this shows the measurement accuracy, the measurement residuals of the lunar laser ranging residuals as a function of time, and you can see originally it was about 1 meter accuracy, and that was limited by the pulse width of the laser beam that goes out. So you send out a laser beam pulse of some width, 10 nanoseconds, 100 nanoseconds, and you get 1 photon back, and you don't know where from along the pulse you got that 1 photon. So the narrower you can make your pulse, the better you can measure accuracy. And so you can see when laser technology improved right here, right? It's a time history of laser accuracy. At this level, though, the measurement residuals are about 2 or 3 centimeters RMS. The measurement precision at the instrument is more than 10 times better than that. And part of the reason the residuals are bigger is because we don't know which corner cube reflected it. But partly it's because the moon wobbles around a little bit, and we can't really model all of that perfectly. We numerically integrate the orientation of the moon, but we don't have a good enough model at the millimeter level to make physical sense yet of all these measurements. So the measurements are ahead of our theory of the structure of the moon at this point.
But each corner cube has a somewhat different velocity because of the...
So if you make enough measurements in a single night, you can get sort of strips from the different rows of detectors, right, and get one of the coordinates. But the other one is harder. Okay, but we currently don't think the dynamics of our knowledge of the moon are good enough to push us to that yet. So lunar laser ranging is, I think, the best way for measuring the ppn parameter beta, although all my French colleagues would disagree. Remember, my uncertainties are bigger than theirs. And the equivalence principle. So the lunar laser ranging tells us about the orbit of the moon relative to the Earth and their relative orbit moving around the sun. And so they can tell that the ratio of gravitational mass to inertial mass is 1, right, to a part in 10 to the 13th. And this says that if we take a weak equivalence principle test from a torsion balance and apply it to this, then we can get a strong equivalence principle test of about the same order of magnitude. And if you believe gamma minus beta minus 4, whatever, it gives you this factor, and you believe that the gamma result from the Cassini measurement, I'll talk about in a minute, then you can infer beta minus 1 is 0 within a part in 10 to the 4th. So you'll see different numbers about this uncertainty in different papers. This is a couple years old, but I think that's about as good as we can do. We've studied various missions concepts to see if we can improve beta or gamma estimates enough to make it worthwhile, to a point where we might see quantization effects of gravity, for instance. But we think we need to do 10 to the minus 9 for that. And we just don't see any prospect for doing that. So let me talk a little bit about radio range. I'm taking longer here than I planned.
So is this Apollo project, right? The LLR? Is that part of what we were showing, or is that out of UCSD?
So there's the Apollo program that launched astronauts to the moon.
Yeah.
There's an Apollo program under the National Science Foundation, which funds lunar laser ranging from Apache Point, which is the AP of Apollo, Apache Point Telescope in New Mexico. Apache Point, APO-LL, Lunar Laser Ranging Observatory. All right, so they get time on that telescope a few times a month.
So it would have been in that plot, basically, in terms of...
Well, and so that's what I call Apache Point. Right, and so the orange points here, which have a little lower scatter than the others, but not a lot, their measurement accuracy is much better than any previous observatory, but we don't know how to fit them yet. All right, and so Tom Murphy at the UCSD is very disappointed in Jim Williams at JPL that he can't fit them better, but he can't. Okay, so for lasers, like I said, you send out a pulse of light to a retroflector and you get a photon back and you measure the round trip light time. For radio range, we're actually sending out a carrier signal at 8 gigahertz, 7.2 gigahertz in fact, up from the DSN to the spacecraft, and it turns around electrically, not with just a mirror, at 8.4 gigahertz. So measuring the change in the phase of the return signal, a function of time, is what we call Doppler. So the change in the phase is proportional to the change in distance, and so we technically do difference range measurements. We don't do velocity measurements, but we call that Doppler because we always take the difference in range divided by time. So it's close enough to velocity. So the Doppler measurement accuracy, the LLR accuracy is limited by how narrow you can make the laser beam, basically. And once you get that and figure out which corner cube you're reflecting from, you're ultimately limited by the atmosphere. So by measuring pressure and temperature of the atmosphere, you can guess what the extra delay due to the refractivity of the atmosphere is to about a millimeter. I don't know of anybody who claims they can do any better than a millimeter. So I think that's the ultimate limit. So people talk about, well, have an observatory in orbit around the Earth to measure, then you don't have to go through the atmosphere again. But how do you know where the observatory is to better than a millimeter? It's very, very challenging. So a millimeter is sort of like my canonical number. For Doppler measurements, we're measuring the phase of the radio signal, and we can measure the phase to about 1,000th of a wavelength practically, just because our analog components in our radio signal kind of fluctuate as a function of frequency. Where in the band you're looking at the phase this particular moment as it moves in orbit around something. So we do about 1,000th of a cycle, and our wavelength's 3 centimeters, so we do about 1,000th of that. So we can measure changes in range like that, and we're limited not by pulse width, but by solar plasma, electrons spewed out by the sun that live between here and Mars. And water vapor in the Earth's atmosphere is important for the radio signal. It's not so important for the optical because the frequency of the laser beams is well above the water vapor resonance. To do range, we put a modulation on this radio signal of a megahertz, basically, which has a wavelength of 300 meters, and we can measure that to about 1/1000th of the 300 meter wavelength. So a fraction of a meter is our measurement precision because of the way that we do the ranging. There's talk for the Bepi-Colombo mission, which will launch next year, to Mercury will carry a 10 megahertz bandwidth ranging system. So they should do a factor of 10 more accurate ranging, and they'll carry multiple frequencies to cancel out the solar plasma delay effect. So they'll be able to measure some things much more accurately than I'll show you here. This 1,000th of a 300 meter wavelength is something that my Russian and French colleagues and I don't quite agree on, because every time we do a tracking pass of a spacecraft or the Deep Space Network, we try to calibrate how long does it take the signal to go up and down the antenna across the cables and through the filters and whatnot. So we do a calibration at the beginning of each pass. And so if you look at the range residuals for each pass, you'll see clumps of points, right, on every different tracking pass that are centered around a different point, right? And the difference in these points is how well the cable delay in the DSN antenna was calibrated at the beginning of those passes. And then, so within that, there's a clumping of noise around here, which is due to solar plasma fluctuations or something. So I consider that all of these measurements are correlated. They all have the same calibration error for every single point, and they all have to be taking that in common. So I only use 1 point from each of these clumps of points because they're effectively the same. Our navigators tend to estimate a bias parameter that then puts them all in common, which is statistically the same. But my Russian and French colleagues treat these all as independent measurements. And so when we do that, there's about 100 measurements per pass, and you divide by the square root of 100, they get 10 times smaller uncertainties than I do. Okay, so the solar plasma effect causes a delay that when you get angularly close to the sun, causes an increase in the delay of the radio range signal. And so this is as a function of time for one particular time on Mars, where here is conjunction, where Mars is on the far side of the sun. And we can't do any radio passes then because we can't get our radios to lock. So these are residuals of the measurement. This is the predicted effect from the solar plasma, and this is the predicted effect from the Shapiro delay due to gamma. So you can see these are kind of correlated. And so your ability to estimate the PP and gamma parameter from radio range right now depends on how well you believe you can fit out the solar plasma. So solar plasma is fairly regular, but you can see you start seeing little signatures when you get there. So how well can you estimate that? Let's see, let me just skip that. So this is, well, we have 10 years, 14 years now of good range data to Mars at the meter level. So we know the Earth-Mars distance for 15 years to better than a meter accuracy. So that's how we know the order of the Earth around the sun or the barycenter to meter level accuracy is from this type of data. Mostly we delete the data near conjunction, but it gets a little noisier during each conjunction. That's when these gaps are. So I think I can estimate the gamma. Well, so this was actually a major experiment proposed for Viking, was to measure the ppn gamma with the radio signal from Viking landers on Mars, which was published in 1976, and they got gamma to 2 times 10 to the minus 3. I think today, or actually 3 years ago from today, we can estimate that's about 10 times better using X-band ranging to Mars for longer. But I don't think we can do better than that. But like I say, my Russian and French colleagues think they can do better. But the best publisher right now is this 2 times 10 to the minus 5, and that's based on using the Cassini measurement, not while it was in orbit about anything, but when it was on its way to Saturn. They picked a quiet period when it went near the sun, and they told the spacecraft, don't fire any thrusters, and don't turn the antenna, and don't do anything. Be as quiet as you can, and look at the Doppler signalers a function of time. And they had a very special radio system because the solar plasma effect causes a signal delay that depends on the number of electrons between you and the spacecraft, but also goes like 1 over the radio frequency squared. So if you can send 2 radio frequencies, you can in principle calibrate that plasma effect out. But it's different on the way to the spacecraft than back from the spacecraft. So in fact, they had to send 2 frequencies up and 3 frequencies back down to cancel the plasma out well enough to do all this. So that's the limit we've got right now. I expect the Bepi-Colombo mission will have a similar radio system, but with wider ranging bandwidth. Should be able to do 10 times better than this sometime after it launches, when it gets on a conjunction on its way to Mercury. So maybe in 2017, 2018, this should be improved by a factor of 10.
So it's different on the way back, not because it's changed, but because you have a sideline as well.
It's changed because the solar wind is sort of blowing across your line of sight as you're looking towards the sun. It's kind of the part that you care about the most. Part of it's flowing directly at you, but part of it's blowing transverse to you along the line of sight to Mars, right? And so it's moving, and so you can sort of think of the electrons as having a Kolmogorov spectrum, random noise, but constrained to an f to the minus 8.3, and so it just moves, right? So from second to second, you would expect to see a different actual integral of the electrons. All right, on the long term, the average is roughly consistent, right, unless you get a coronal mass ejection or something. Okay, so the precession of the perihelion of Mercury is a famous experiment for general relativity. It's easier for us right now to look at the precession of the perihelion of Mars, although we're starting to look at Mercury more carefully. So I think we can measure based on the precession of the perihelion of Mars using this equation. We get beta minus 1 is 2 times 10 to the minus 4, which is about twice as bad as the lunar laser ranging data. And this is a bigger uncertainty than my French colleagues have published basically recently. Okay, people care sometimes about time variation of G. Well, we can't really measure the time variation of G. We can measure the time variation of the GM of the sun. Right? We can measure the GM of the sun absolutely to about a part in 10 to the 11th. We can tell its rate of change, the fractional rate of change, to about a part in 10 to the 13 per year. So in some sense, we don't believe G is changing that much. But at a much lower level, we have to worry about the mass of the sun itself is changing, right? It's spewing out photons all the time. And so it should be changing by almost this much per year just by spewing out photons, although it sucks in some asteroids and comets to compensate. So somewhere around here, we can't tell anything more about G doing this type of an experiment.
The solar wind, isn't that bigger effect?
Sorry?
The solar wind?
The solar wind, the electrons and the protons is, I think it's less than 1% of the photon mass energy. It might be 5%. I don't remember the number that well. The photons are the biggest part, right? And the solar wind matters, but there's a mass influx too of dust, which is about comparable to the solar wind. Okay, we look some of the inverse square law violation. This was a big area of study back in when I was in graduate school in the 70s. When was that? Anyway, some guys published that they saw a deviation from 1 over r squared for going up a tower on Earth. I don't know if any of you remember that. It was very controversial. Nobody else could find what the problem was. We all knew it was wrong, but NSF put a lot of money into trying to develop experiments to measure it better. So I don't know if you've seen this kind of plot. Show that if you have a Yukawa potential, then a typical experiment can, for a given length scale, constrain the Yukawa parameter. So different experiments can constrain the Yukawa parameter at different length scales differently. So from lunar laser ranging or from Cassini ranging, we can exclude this range of deviation from 1 over r squared. I think So eventually, for those of you who don't know, the people who did this original experiment, somebody finally dug through all their data and they found that the reason they saw a deviation from 1 over r squared was because they did their experiment in a marshy area and they very carefully did all their measurements on the dry parts. And so they didn't uniformly sample all the parts of the local terrain. And so they biased their result for the dry relative to the wet and got a tidal term they didn't take into account. But they were like 10 years of people working very hard to prove that they were right or wrong. It was amazing. Fifth force, they call it. So I think now there's a lot of effort, or some effort, to measure deviation from 1 over r squared at the millimeter scale. And people here know much better than I. But at the long length scales, we know that 1 over r squared is good. So I think I'll wrap up with this. So something I meant to mention earlier that I didn't was that if we measure Doppler in range to a spacecraft. So if we have Doppler measurements of a spacecraft going around Mars with a 2-hour period, then the Doppler signature that we get relative to the noise in the measurement allows us to determine the position of the spacecraft relative to the center of mass of Mars to better than a meter. So we can use the range measurements to the spacecraft at the meter level to measure other things like the ppn gamma or the beta to a meter. But as the spacecraft gets farther from the planet, like Venus Express spacecraft, I have some data on, is in a 24-hour orbit. And so its orbit, its Doppler shift at periapsis is comparable to the Doppler shift we get from the Mars orbiters, but at apoapsis it's a much slower rate of change of velocity, and so the Doppler signature is much smaller. So the longer the orbit period, the less well you know the orbit of the spacecraft. And so your ability to use range measurement to the center of the planet, mass of the planet that you're orbiting, is not as good. So for Venus, we currently use Venus Express spacecraft, and our range measurement residuals are not a meter, they're about 10 meters. And the reason it's not because the measurement's worse, it's because the orbit of the spacecraft is not as well determined. So I had a postdoc here last year. We were working on Cassini range residuals. So Cassini is a spacecraft in orbit around Saturn with a period of orbit that varies from about 2 weeks to about 5 weeks. So with a 2-week orbit, the Doppler shift of the signal is not so good. And so our ability to know the distance from the spacecraft to the center mass of Saturn is, at the sort of 50-meter level. And for a long time, we were trying to solve for the orbits of the spacecraft and the orbit of Saturn, and we just couldn't figure out why we were seeing this annual signature in our data. But finally, we figured out we had to throw all the range data out when we solved for the position of the spacecraft, so we could use the range data to tell us where Saturn was. But it took us a long time to figure out how to get that done right. But this is the result of the process, is that we can measure the range to Saturn now, not the spacecraft, but Saturn, with sort of this level of accuracy, and the noise gets worse later in the mission, partly because it's not in the prime mission anymore, is when it was just launched, and you have to do the science. After that's an extended mission, they don't pay you as much anymore. So they don't track it as much, and they also sent it into a shorter orbit period, so we got less Doppler measurements. So the orbit of the spacecraft's not as well determined here for the last few years. So doing this, my postdoc here wanted to say, looking at the modified Newtonian gravity, which is a deviation from 1 over r squared gravity that can explain spiral arms in the galaxy wrapping up. And so the Mond theory brings a tidal force on the solar system from that type of an effect that we can measure. And so using this data, we just got accepted today. A paper says, well, Q2 is less than this 10 to the minus 27 per second squared. And that basically rules out almost all possible Mond theories that depend on that type of an interpolating function for the 1 over r squared. So the originator of the theory says, well, yes, that's true, but if you modified inertia instead of the force, then it would be different. So we can't say anything about that. But in terms of modifying the equations of motion, like 1 over r squared, there's no Mond acting in the galaxy. So,
do you know if this, the Pathfinder experiment, is it the same effect?
Pathfinder.
The proposed LISA Pathfinder experiment?
I don't know that they've talked about doing anything with Mond, and if they have, I don't know what it is.
No, they have. I don't remember the details, but it's about sending it in extended mission to the gravitational settle point.
That's something different. Yeah, let me think. I remember arguing that with Stefano. It's not the same effect. This is sort of a tidal flow across the solar system, and that's not what you see at the saddle point. You're sort of seeing whether the Earth's gravity and the Sun's gravity balance exactly with the extragalactic gravity. I'm not sure exactly how that works, but it's not the same. Okay, so I think I'll wrap up here. I had some backup slides to show for different planets how good we do and whatnot. But I think it was the gravity aspect that I meant to get across here. So hopefully you learned something you're interested in. But I'll wrap up there.
There's been various claims about NASA using optical laser tracking, which would avoid the solar plasma and such things. Is that likely to happen anytime soon, or what prospects do you think that would bring?
Am I free to answer that, Joe? I'll try to be politically correct here. Laser comm on a mass per mass and a watt per watt allows you equal basis, allows you to get more bits back from one place to another than radio. It just allows you to focus the energy tighter, and so you get a higher rate of data down. And so I think laser comm is currently in use, probably in some Air Force satellites that we don't know about. ESA's trying to build them into their TDRS network to connect in between geosynchronous satellites, and it's very effective there. There's a lot of people at NASA who would like to put this on a mission to Mars or Saturn or some other satellite because it's neat. All right? And if you could have it on Mars, and you could get pointed accurately enough, and you could filter out the sunlight well enough, then for the same amount of watts, you could send back, I don't know, 1,000 times as much data. Right? So I think when I hired on to JPL in 1988, they told me to work on that problem, to do radio science with laser comm. And after a couple of years, said, you know, there's probably not going to be one very soon. So today I would say, I think there will be a laser comm terminal on one Mars satellite in the next 20 years. That's my best guess, maybe in the next decade. I don't think there's any talk about doing it on the 2020 mission. There's some talk about making the next Discovery mission carry a laser comm package. Right, but it's talk. So the technology guys would like to push it. The planetary scientists would rather not carry the extra mass. And so I don't know how that will go. But I worked with Slava Tereshchev and some others to study what could we do if we had a laser comm terminal. So it turns out in terms of Doppler measurement, which is what we use to measure the orbits of the spacecraft mostly and the gravity field of the planets, you can't do any better with Doppler than you can with radio, because you're limited by the troposphere. So the X-band Doppler is limited by the wet troposphere in the end, but Ka band radio is not. If you calibrate the water vapor out, you can do just as well as any laser could. So the only thing that I think you can do better with a laser in terms of measuring distances or changes in distance is range. And so we can measure absolute range maybe to something on Mars to a millimeter is the best we could do, I think, going through the Earth's troposphere. The dry troposphere, we can't calibrate better than that. So we should be able to measure ppm gamma better with the laser. Okay, and our study simulation showed that we could measure ppm gamma a few parts in 10 to the 8th. But that's about the only science I think you can do with a laser that you can't do with a radio signal. Okay, well, thank you all for coming, and have a good evening.